We talked about how you can graph sines and cosines and how we can graph transformations of sines and cosines. And now I want to talk in this video about how can you go about graphing other trig functions. So what about the graphs of the other trig functions? How could you go about making those graphs? Well, the ones that I want to start with are, I want to think about cosecant and secant. So if I wanted to graph y equals cosecant of x, the way that I can do this is I can remember this is just going to be 1 over sine x. Now, remember that secant and cosecant, those are the reciprocals of cosine and sine. And the trick for remembering this is that the co flips. So cosecant goes with regular sine, and regular secant goes with cosine. Well, the thing is that this means if I make a graph of sine x, all I have to do is think about what does the reciprocal of that graph look like. And so let me make just a little sketch here of sine of x. So we're going to say this is at pi over 2. I'm sorry, that should be pi over 4. That's the first point that I want. Then we're going to have pi over 2. Then we're going to have I did want pi over 2. Yes, pi over 2, then we want pi, then we want 3 pi over 2, and finally we want 2 pi. Sorry about that. I don't know what was getting in my head with that pi over 4 there. Now, sine is going to look like this. So it comes up to 1, comes back to 0, down to -1, and back up to 0. And it keeps on going in this manner off in both directions. Well, what is the reciprocal of this thing going to look like? The reciprocal here is going to, at pi over 2, it's going to also be equal to 1 because the reciprocal of 1 is still 1. And at 3 pi over 2, the reciprocal of -1 is still just -1. Now, let's take this pi over 2 spot here. As I move on either side of this pi over 2, sine is getting smaller. So what happens to the reciprocal? It gets bigger, right? We look on either side and we start getting bigger. And so we get this kind of U shape going upwards like this. And as the sine function approaches a value of 0, this fraction, this reciprocal, is going to blow up. So we're going to actually get a vertical asymptote here and another vertical asymptote at 0. And this U shape going upwards. Over here, same kind of idea, except this time we're going to get a U shape going downwards. And the vertical asymptotes, it's going to go to the vertical asymptotes going downwards because it's negative. And so what we end up with for this graph is we're going to end up with this picture that has a vertical asymptote at 0 and at pi, at 2 pi, and so on. So every multiple of pi, we get a vertical asymptote. And then it has these U shapes with up U and then down U, up U and then down U. So that's the basic shape of the cosecant. Now, of course, from this, you can start making other kinds of pictures as well about the cosecant. So, for example, assuming I can find my eraser, there it is. If I wanted to graph something like, let's say, y is equal to the cosecant of, let's do pi times x divided by 2. Well, the way that I can do this is, let's think back for a moment here to the way that we did this when we thought about sines and cosines. We had to look at what is the new period. So the new period is going to be the old period divided by the coefficient of the variable. In this case, that's the coefficient of x. So in this case, this new old period was 2 pi, and the new period's the coefficient here is going to be pi over 2. So 2 pi divided by pi over 2. This is 2 pi times 2 over pi. My pi's cancel, and I get 4 for the new period. So this is going to be a cosecant function, and there's no other transformations to worry about. All we have to do is to change the period. The new period is going to be 4. Okay, so what is that going to end up looking like? Well, it's going to be exactly the same picture as we had before, which hopefully you guys have still in your notebooks, because I had to erase it, of course, except instead of going 0, pi, and 2 pi with my vertical asymptotes are going to be at 0, and then a full period would be out at 4. So we get another vertical asymptote at 4, and in the middle, I have a vertical asymptote at 2. And we have the vertexes or vertices of our U-shapes are going to be halfway in between each of these vertical asymptotes. If you look back at what the graph looked like, they're halfway between the asymptotes. So that's going to be at 1 and at 3. Otherwise, we just get this U shape here. And if you want to keep on going, you can. So for example, over here on the left, I could extend this, and I would get another upside down U shape over here. If I want to keep on going on the right, I would get another another right side up U shape over here, although I don't really have a lot of room to keep on going, so I'm going to stop there. Now again, refer to your book. All of this stuff is in, I believe, 7.7, and that will show you much nicer pictures of these graphs than what I am able to do here without a computer. You know, I'm just giving you a little hand sketch. Doing this with a computer is really helpful. By the way, when you're doing these graphs, don't forget about Symbolab as a tool that you can use. Now, I'm not saying you shouldn't rely on this, okay? I don't want you to get into the point where you can't actually figure out how to do anything if you don't have access to Symbolab and you need to make a graph. But what I do want is I want to make sure that you know that you can refer to this so that you can double check yourself. And so that if you are totally lost, you can say, okay, I want to have some idea of what it is that I'm going for. The thing is, once you see what Symbolab gives you, you need to understand why that's what you get. Okay, so that was an example with cosecant. Let's take a look at what happens with secant. In fact, I'm going to strongly advise here that you pause this here and take a couple minutes and see if you can work out what a basic graph of y equals secant x would be equal to. And as a hint, remember that secant is 1 over cosine x. So what you want to do is graph cosine and then try to graph the reciprocal of that function. Okay, so hopefully you guys were able to figure that out. Let's go through it together, though, just to make sure. Remember what the cosine function looks like. It actually looks very similar to the sine function, except that it's been shifted over by pi over 2. So the cosine function, it still fluctuates between +1 and -1. And the period is still going to be 2 pi. We'll mark halfway, we'll mark pi over 2 and 3 pi over 2. It starts at the top, it comes down through 0, hits the bottom at pi, comes back up through 0, and it comes back to the top at 2 pi. And it keeps going like this on either side. So over here at minus pi over 2, we come back through 0, and so on and so forth. I'm not going to keep on going too much further here, but there is a reason why I actually am marking things out over to a little further here. So What happens when I take the reciprocals? Well, wherever the original function is equal to 1 or minus 1, the reciprocal is 1 or minus 1. So those points aren't going to get moved, but everything else is going to be taken with the reciprocal, so it's going to get flipped and stretched. So if I start here around x equals 0, as I move on either side, the reciprocal of this value is getting larger and larger. As this value gets close to 0, we get a vertical asymptote, and we go up towards infinity. So again, just like with the secant, remember what we had with the secant was still, we had this kind of U shape going on here. It was just shifted a little bit further to the right. And that is exactly what we would expect, because cosine and sine, they have very similar graphs. They're just shifted. Well, from here, the rest, again, this is kind of like what we saw with cosecant. We're going to get an upside down U there. We're going to get another right side up U over here, and so on. So if you wanted to, strictly speaking, just graph it on, whoops, I'm sorry, that should be coming up here like that. I'm having trouble with making everything to scale here, but one period literally only goes from here at 0 over to 2 pi. So if you only graphed one period, you'd get an upside down U in the middle, and you'd get half a U on the left and on the right. But when you start extending the graph, I think it's easier to see what's happening here, because then you really see how, oh yeah, it's the same as what we did with the with the cosecant. It's just that, well, now everything has been shifted by pi over 2. Just like when we go between sine and cosine, everything gets shifted. All right, so this takes care of what does the basic graph of secant look like. Now, just like with anything else, you can do transformations on this kind of thing. So I will encourage you guys to look at the examples in your book and watch the examples that my math lab has in their videos to see some examples of transformations on these kinds of functions. But I want to go on to talking about cotangent and tangent. Well, actually, we're going to start with tangent, and then we will do cotangent. So what if I wanted to graph y equals tangent of x? Well, let's think about what this function does in terms of the unit circle. Now, there's a couple of things to notice here. The first thing to notice is that this has a period of just pi. It no longer has a period of 2 pi. You have to go back to look at where we found that, but this really only has a period of pi, as we've talked about. The other thing to notice is that if I want to get this thing into a full range of what it does, remember that this is really sine x over cosine x. So it's actually going to be, I can think of this as, it is, if I think of this as sine theta over cosine theta, and I think about the terminal point, then this would be the y value of the terminal point divided by the x value of the terminal point. So yes, let me go back here and actually let's try to graph y equals tangent theta, which is sine theta over cosine theta. That way we don't get confused here with our x's and y's. That would probably, I should have done that from the start, but I don't feel like re-recording this whole thing. So if we sketch a quick unit circle here, we can see that what is going to happen is that at this point here, at an angle of 0, so let's make our theta versus y graph here. At an angle of 0, the sine divided by the cosine is 0 divided by 1 or 0. In other words, this thing is going to go through 0, 0. Well, what next? Another thing that we can say is that at pi over 4, and at negative pi over 4. Here, what we have, and I apologize for the glare that is making that hard to read. Hopefully you can sort of see that. Here, the terminal point is square root 2 over 2, comma, square root 2 over 2. Here, it is square root 2 over 2, comma, negative square root 2 over 2. Okay, so what is the ratio at those two angles? Well, the ratio here is 1 and minus 1. So, let's try to mark those points in. At an angle of pi over 4, we are going to go through the y value of 1. So at pi over 4, comma 1, we're going to go through there. And at minus pi over 4, we're going to go through minus 1. So we have this point minus pi over 4, comma, minus 1. Now, let's do the top half first. As I keep increasing this angle towards pi over 2, the y value is approaching positive 1, and the x value is getting close to 0. In other words, the numerator is blowing up to 1. Well, it's not really blowing up, but the numerator is getting close to 1. The denominator is getting close to 0, but they're both positive. And that means the fraction is blowing up towards positive infinity. So at pi over 2, I'm going to get a vertical asymptote, and this is the kind of picture that I'm going to get. It's going to sweep upwards towards that vertical asymptote. Over here, at minus pi over 2, the opposite is going to happen, because now the numerator is getting close to negative 1, and the denominator, the x value of the terminal point, is getting close to 0 but remaining positive. So, we're going to get this picture that goes down towards this horizontal asymptote. We get this sort of snake shape here. And the thing to keep in mind is that we've now graphed from minus pi over 2 to positive pi over 2. Since this is periodic with a period of pi, everything else on here is going to look just like this. So if I wanted to go over here from pi over 2 to, let's say, pi, what I would see is this snake shape would come up and it would hit 0, and then it would keep on going. And if I had more room here instead of a hallway, I would get another vertical asymptote at 3 pi over 2. If I wanted to keep on going to the left, again, I would just get another copy of this snake shape. So that's what we get for the tangent function. We can work out the cotangent in a very similar way. There's actually a few different ways we can think about the cotangent, but personally, I think the way to do the cotangent, probably easiest to just think about it the way we just did. So we can say, what if I want to graph y equals cotangent theta? Well, this is cosine theta divided by sine theta. So let's think about this one. Now, again, make a quick sketch of our unit circle. That's a terrible unit circle, but that's okay. We just want to have the basic idea. And then we're going to graph, and let's move that center line up a bit, y versus theta. Okay, so what's going to happen here? Well, this is going to be the x over y of the terminal point. So we take the x coordinate of the terminal point and then we divide it by the y coordinate of the terminal point. So one thing that we can say immediately is that up here, and remember this is a right angle, so an angle of pi over 2, that's going to be where I hit 0. Because here the x value is 0 and the y value is 1. 0 over 1 is 0. Now, what happens as the angle increases from there? Well, as it increases, x is negative, and y is going to be still positive. So we're going to get a small negative number divided by a positive number. So it's going to be decreasing. And when we hit 3 pi over 4, that is going to be where we go through the point -1. Because that is where the numerator and the denominator have the same absolute value here, just like when we were dealing with the tangent. And as we keep on going up towards an angle of pi, we see that we get a vertical asymptote, and this fraction blows up towards -infinity. So what I get is a picture like this. What about if I start at pi over 2 and I start coming back this way? Well, at pi over 4, I'm going to go through the point +1, and then at 0, I'm going to have a vertical asymptote. So what I get, it looks kind of like the tangent function, except that it has been flipped upside down and shifted by pi over 2. But it's the same basic snake shape. And once again, you're going to get the same shape repeating forever in both directions. So you keep on getting this same pattern going off every time you move by an interval of pi. Once we have this one interval graphed, we get everything else for free. Again, look in your book for some slightly better graphs of this maybe. Now, if we want to make a graph of something that, say, the start has been shifted as well as the period, and we're dealing with something like this, like let's say that I want to graph y equals the cotangent of, let's say, that is really bad looking. Let's do pi times x, and then we will do plus, let's say, 1. Actually, let's make things a little easier on ourselves. Let's do plus pi over 8, just for the sake of example. I want this number to not be too bad. I just want to show you the idea here. So let's say that we want to graph this thing. Well, the thing is that the new period is going to be the old period of pi divided by this coefficient of pi, which is equal to 1. So the new period of this thing is just 1 in this case. And where does it start? Well, to plug in 0, we would need pi x plus pi over 8 to be equal to 0. So this is going to mean that pi times x equals negative pi over 8, and this gives me x equals negative 1/8. So what used to be at the origin has been shifted over to negative 1/8. And with this information at hand, I can make my sketch. So I know that my what used to be at the origin is now at negative 1/8. And we will complete a period after 1, so that's going to be over here at 7/8. Because negative 1/8 plus 7/8 gets me over to, or negative 1/8 plus 1 gets me over to 7/8 is what I'm trying to say. Okay, now what I know about cotangent. Well, at the origin, it would normally have a vertical asymptote. So that vertical asymptote is now at negative 1/8. And it would also have a vertical asymptote at the other end here at 7/8. So remember that what we have here, if we go back to thinking about what we just did, the cotangent is the x value divided by the y value. So around an angle of 0, x is close to 1 and y is close to 0, so it's blowing up. Now, we know that halfway through here, which is going to be at the point 3/8, that is where we go through 0. And at 1/4 of the way through, that's going to be at 1/8. That is where we go through 1. 3/4 of the way through, which is at 5/8, that is where we go through negative 1. But we get a sort of a snake shape regardless of all those changes. So I just connect these things up in a sort of a snaking fashion. That's a very ugly sort of graph, but hopefully you get basically the idea of what I did. I mean, the actual graph is not ugly. It's just my particular rendition that's kind of ugly. And then, of course, this pattern is going to just keep on repeating forever in both directions. So you keep on shifting this over by intervals whose width is 1, since that's the new period, and that gives you your graph. Now, we don't usually worry as much about graphing the other functions than sine and cosine. And one of the reasons for that is because sine and cosine turn out to be really useful for analyzing other functions. In fact, it turns out that you can kind of express all nice functions in terms of sines and cosines in a kind of complicated way. For most of you, you don't need to worry too much about this, but I mention this for those of you who are going on to take calculus, that in calculus, you'll see much more about how does sine and cosine relate to all these other functions, if you go into Calc 2 in particular. But it turns out that the other 4 trig functions, the secant and cosecant, the tangent and cotangent, we don't care so much about all the different transformations of them. So you want to know how to do them, and doing them is really no different than what we did with sine and cosine, but it's not something that you have to do nearly as often as working with sines and cosines. In particular, for example, sine and cosine are very useful if you are interested in, say, acoustics. You can break down any sound wave into various sine functions with different periods. And you can break down any, let's say, electronic signal into something with various periods. So anyway, yeah, sine and cosine are the things that are the most important to kind of understand how to do. Those are the ones that are most commonly used, but you do want to know how to do stuff with this as well. All right, so I think that's everything I wanted to say about these particular graphs. Make sure that you guys practice the problems from 7.7 that are going to be in your homework. Well, also do them to submit, but I really want you guys to be practicing that sort of thing. And I will put up another one of these videos in a couple of days.